Hello everybody. In this video we are going to start talking about sound. Now this is a rather lengthy video. Sorry about that. And I don't expect you to sit through the whole thing in one sitting. So I've broken this down into 3 different sections. And we're going to spend the next 2 weeks or so talking about sound. And we're going to have a test on waves, vibrations, and sound on or around May 22nd. So I've broken this down to 3 sections. We're going to be covering each one of those separately over the next 2 weeks. The first section that we are going to cover is on the speed of sound and the intensity of sound. And we're going to be covering that topic on May 11th and 12th. It covers slides 2 through 13 in this presentation, and I will also put the times for those slides once I get the entire video recorded. So you should have at least that section of the video watched before May 11th. Starting on May 13th and going through May 15th, we are going to be looking at the Doppler effect. That covers slides 14 through 18 in the presentation. And again, I'll put the times for those slides on here as well. But you should have at least slides 14 through 18 watched by May 13th when we start to talk about the Doppler effect. The final topic that we're going to talk about is resonance and standing waves. And we're going to be covering that topic from May 18th through the 20th. It covers slides 19 through 30 in the presentation. Once again, I'll put those times here. By the way, I'll put all of those times down in the description below, so it'll be there for you as well. So you should have this last part of the presentation watched somewhere or sometime before May 18th. So we're breaking it up for you, so you don't have to watch too much of this all in one sitting, and that would just kind of rot your brain, and we don't want to do that any more than we have to. The first thing we want to talk about is how a sound wave is produced. Now, usually I have this slide up and I do a lot of really cool demonstrations in class with a tuning fork. Sorry, you don't get that with the 2-dimensional Tiesler. That only comes with the 3-dimensional Tiesler. But there's a couple of things on this slide that I do want to make sure that you guys are aware of. The first thing that we need to know is that sound waves are longitudinal waves. And remember, a longitudinal wave is one in which the medium the wave is traveling through vibrates in the same direction or parallel to the direction the wave is traveling. So instead of going up and down while the wave goes back, travels from left to right horizontally, the medium is also vibrating horizontally if the wave is traveling horizontally or vice versa. So that's what a longitudinal wave is. The other thing that I want you guys to take away from that is that sound waves need to travel through some form of a medium. There needs to be some kind of medium for the wave to travel through. Usually, like right now when you're listening to the melodious sound of my voice, the medium that it is traveling through is the air. The sound is coming out of your computer's speaker or your phone's speaker, and it is traveling through the air and then hitting your eardrum and causing that to vibrate, which you then sense as sound. So that's another important thing. Now, we associate sound traveling through air, but sound can travel through any medium. Sound can travel through liquids like water. Sound can travel through solid objects like the earth, like metal. So it can travel through any type of medium, and the type of medium does affect the speed with which the sound wave travels. And usually I have tuning forks to demonstrate all of this stuff, so you'll just have to kind of bear with me explaining this. But when we use a tuning fork to produce a musical note, works with any kind of object that you want to use to create a sound wave. If you want to go into your kitchen, grab a couple of the lids to some pots and clang them together like you did when you were 5 years old. Actually, don't do that. I'm going to get angry emails from your parents if you do that. Scratch that idea. Don't do that. But it's the same exact thing that's happening. When you do that, what happens is the metal or the material, whatever material it is going to vibrate. It's going to vibrate back and forth. And it's that vibration that causes the sound wave or creates the sound wave. And it creates a sound wave by disturbing the air around it. So you can't see it vibrating because it's happening at a very small level, but it's still creating areas of high pressure and low pressure that we perceive as sound. So if I were to do this with a tuning fork, the forks, or what we call the tines of the tuning fork, which are these guys right here, are going to vibrate back and forth. So they're going to want to both vibrate back and forth. When this tine here vibrates to the right, it's going to smush or compress the air molecules next to it, and it's going to create a region of higher density, or the air pressure in there is going to be greater than the surrounding air molecules. This is our area of compression, what would be analogous to the crest of a transverse wave. When the tine of our tuning fork moves back in the other direction, in this case to the left, it's actually going to create a region of lower density. It's going to cause the air molecules to spread further out, and it's going to create this region of lower density air molecules, and we call this an area of rarefaction. And this would be analogous to the trough of a transverse wave. And it's going to be vibrating back and forth like this hundreds, sometimes thousands of times a second, and it's going to create this succession of high density regions and low density regions that are then going to travel through the medium, in this case air, until it reaches something like our eardrum, and that's what we would perceive as a sound wave. Just to recap what I just said in this diagram, remember that in this case, our tuning fork is going to be vibrating hundreds, if not thousands of times every second. And every time it does that, it's going to create these alternating regions of higher and lower density. And where we have our regions of higher density here, which we call our areas of compression, that is going to be analogous to the crest of a transverse wave. Where we have these regions of lower density, those would be analogous to the trough of a wave, and we call those areas of rarefaction. Let's talk about some categories of sound waves. The first category I want to talk about are audible sound waves, and those are the sound waves that fall within the range of human hearing. And that is normally between about 20 hertz and 20,000 hertz. Infrasonic sound waves are frequencies that fall below the range of human hearing, of what we can't hear. Very, very low frequency sounds. Elephants can make infrasonic sounds that we cannot detect. Researchers who studied elephants in the wild always used to be amazed that elephants that could be miles and miles apart, not within sight of one another, would coordinate their movements to meet up at specific places like watering holes, things like that, and they couldn't figure out how the elephants were communicating until somebody figured out that they were using infrasonic sound waves, which, by the way, can travel much further than higher frequency sound waves. Another category is ultrasonic waves, and those are waves that are above the range of human hearing, so usually above 20,000 hertz. A couple of examples of those are dog whistles. Right? Dogs can detect that range of sound, but our ears cannot. And another good example of that are ultrasounds, if you ever had one for a medical procedure that uses sound waves that are above the range of human hearing as well. Let's talk about our first formula. We're 7 slides into this sucker? Might as well be doing some math by now. I want to talk about how fast sound waves travel in the air. One of the unique features about a sound wave is that how fast it travels is dependent upon the temperature of the air, because the temperature affects the air's density. So our formula to find out how fast a sound wave is going to be moving at a particular temperature is that the speed of the sound wave, which is our v here, that is the velocity of the sound wave, is equal to 331 meters per second, and that number, 331 meters per second, is the speed of a sound wave at 0 degrees Celsius. So our velocity of a sound wave is 331 meters per second times the square root of the air temperature in Kelvin divided by 273 Kelvin. So remember, whenever you plug a temperature into this formula, it has to be the temperature in Kelvin, not degrees Celsius. If you're given the temperature in degrees Celsius, and you will, you're going to have to convert that into Kelvin. And that's a simple procedure. If you guys remember that from our study of thermodynamics, to convert Celsius to Kelvin, you simply add 273. To convert from Kelvin to Celsius, you subtract 273. I'm not going to spend a lot of time talking about the intensity of a sound wave. It's not really a main focus of what I want you guys to get out of sound. I just want to cover it briefly because it is important, but we aren't going to spend a lot of time talking about it. One thing to remember about waves is that waves transfer energy from one place to another. So the intensity of a sound wave is related to how much energy is being transferred by the wave. So what we need to know for intensity is the rate at which energy is flowing through a given area over a given amount of time. And we usually orient that area that we're measuring perpendicular to the direction the wave is traveling. So our intensity is equal to 1 divided by the area, sorry, here, let's try this again. So equal to 1 divided by the area times the change in energy divided by the change in time. Now remember, this change in energy by the change over the change in time is equal to my power. And this funny looking guy here is just a fancy little p, and we could just relate that as power. So the intensity equals the power divided by the area. So it's the rate at which we're transferring power or energy from one place to another. And the units that we use for intensity are going to be watts per meter squared, because my units for power is watts and my unit for area is square meters. So that is going to be my formula. Matter of fact, I can't think of an instance where I'm going to give you the center part of this formula, so we can just kind of rewrite this as intensity is going to equal the power divided by the area. Just to give you guys a couple of examples of different intensities of sound, the threshold of human hearing, the lowest intensity that we can detect, or the faintest sound that we can hear, is about 1 times 10 to the minus 12th watts per square meter. So that's a very, very low intensity. Our ears are actually very, very sensitive instruments. The threshold of pain, where hearing gets to be painful, which coincidentally must be the intensity of my first wife's voice, is going to be about 1 watt per square meter. And that is the loudest sound that humans can tolerate without feeling or experiencing pain of some sort. And like I said, our ears are actually very, very sensitive when it comes to detecting sound waves. And we can detect, our eardrums can detect different pressure fluctuations of about 3 parts in, I think that's about 100 billion. So very, very small fluctuations in intensity we can detect. One thing about the intensity of sound waves, or how we perceive the loudness of a sound wave, is that it is a logarithmic scale. Now, don't freak out. We're not going to do logs in this class. There's going to be no math with logs. The only reason I'm bringing this up is that because we measure this intensity in a unit called decibels, and that is what we're kind of familiar with when we talk about the loudness or intensity of sound waves. We always talk about the decibels of, or the decibel level of the sound wave. So that is why I am covering that. But we are going to do no math with a logarithmic scales, or no logs in any of our equations. I included the equation here just to show you what a decibel is. But matter of fact, I'm just going to, here we go. We're going to get rid of this right now because we are not doing any logs in this class. But just know that the sound or sound waves or loud, the intensity of sound waves is what I'm trying to say, is a logarithmic scale. That's the one thing that I want you to know from that. And we measure that in decibels. This is a table that shows you the intensity of different types of sounds, both in decibels and in terms of watts per square meter. So if you're talking a normal conversational tone or normal volume for conversation, that's going to be at about 65 decibels, or about 3 times 10 to the minus 6 watts per square meter. That's just normal conversation of the intensity of sound coming in at normal conversation, two people talking that are about maybe half a meter apart. A whisper is at about 20 decibels, and that's about 1 times 10 to the minus 10th watts per square meter. Our threshold of hearing is at 0 decibels, and as I said before, that's about 1 times 10 to the minus 12th watts per square meter. If you hear a siren, or if you're not too far away from a siren, that's usually at about 100 decibels, or 1 times 10 to the minus 2nd watts per square meter. And remember, this is a logarithmic scale, so these things are increasing exponentially. A rock concert is at about 120 decibels, which coincidentally is our threshold of pain. And if you are 30 meters away from a jet plane with its engines going full blast, and why would you be? But if you are, I guess maybe if you work on the tarmac, that's why those guys have to wear hearing protection, that's at about 140 decibels. Just want to talk a little bit about how we graphically represent a sound wave, because we can't actually see sound waves, so we have to find some way to represent these graphically, and we're going to come back to some of this stuff when we talk about optics in a few weeks. When we talk about a sound wave, we like to talk about what we call a wave front. And a wave front is a concentric arc that travels away from the source, or travels with the sound wave. And sound waves usually travel radially out from a source in all directions. So if we have a wave front here, that is going to be separated from the next wave front by 1 full wavelength. So we can kind of correspond wave fronts with the crest of a wave, or the areas of compression of a wave. It really could be any part of the wave, but we like to associate them with the areas of compression. They are 1 wavelength apart. And then we also have rays that travel out. Let's try this again. Rays that travel out radially from the source, and these rays are going to be perpendicular to the wavefront. So my rays are always perpendicular to a wavefront. And we notice that when we have a wavefront that is fairly close to our source, like right here, we can see that the rays are definitely going off at different angles. As we get further away from the source, the angles between the rays becomes less and less. As a wavefront moves farther and farther away from the source, essentially the circle that it makes gets bigger and bigger. And when that happens, the arc of the wave gets less and less until you get far enough away, and then the wavefront becomes almost a straight line, and the wavefronts are almost parallel to each other. They almost become parallel planes to one another. And because my rays here are perpendicular to the wavefronts, if my wavefronts are nearly parallel planes, then the rays are going to be nearly parallel to each other. Not completely parallel, but nearly parallel to one another. That'll come in a lot more important once we talk about light and optics, but it's just one thing about sound waves that I wanted you guys to know. Now I want to move on to something called the Doppler effect. Now, the Doppler effect is the effect that happens whenever there is motion between the source of a wave and an observer. We're going to be talking about the Doppler effect as it relates to sound waves. In a couple of weeks after Memorial Day, we'll be talking about how the Doppler effect relates to electromagnetic waves or light. But for now, we're just going to limit our discussion to the Doppler effect and sound waves. This is something that we've all experienced a lot, and it's kind of second nature to us. But if you've ever noticed, if there is, say, an emergency vehicle passing by, a police officer or a fire truck or an ambulance, you can hear the pitch or the frequency of the sound wave changes as that vehicle gets closer to you and as it moves away from you. And if the source of the sound wave and the observer are moving towards each other, the observer is going to hear a higher frequency sound wave than what is being emitted by the source. when the source and the observer are moving away from each other, the observer is going to hear a lower frequency than the sound wave that is being emitted by the source. Just to reiterate what I mentioned in the previous slide, we're going to be looking at the Doppler effect as it relates to sound waves for now. Just want you guys to know that the Doppler effect happens with all types of waves, and we're going to look at how the Doppler effect works with electromagnetic waves in a couple of weeks, but right now we're just going to be dealing with how it affects sound waves. But I do want you guys to understand that the Doppler effect is something that is, or something that occurs with all types of waves. Let's take a look and see how the Doppler effect works if an observer and a source are moving toward one another. So if I have a source of a sound wave here, it's emitting the sound wave, and these wave fronts are moving away from the source. If you have an observer that is moving toward the sound wave, what's happening is the sound wave is moving in this direction. My observer is moving in that direction. The observer is going to be passing through these wave fronts with a greater frequency or quicker than he would if he were standing still or stationary. So that is why he hears a higher frequency, because he's passing through more of these wave fronts because he's moving closer. In a sense, he's just shortening the distance between successive wave fronts. If the observer and the source are moving away from each other, the opposite thing occurs. As the wave is traveling, we see the successive wave fronts here, but as the wave is traveling from the source, the observer is moving away from the source as well. So when this wave front intersects with the observer right here, by the time this next wave front reaches the observer, their position is going to be changed and they are going to have moved further away. So it's going to take longer for this wave front here to intersect with the observer. So they're going to experience fewer wave fronts and they are going to hear a lower frequency. And by the way, the term observer simply means the person perceiving or hearing or receiving the sound wave. That's what observer means. Let's look at our equation for the Doppler effect. Now we could have the source and the observer moving towards each other. Now I could have the source be stationary and the observer moving toward the source. I could have the observer be stationary and the source moving toward the observer, or vice versa. I could have the source be stationary and the observer moving away, or the observer stationary and the source moving away, or they could be both moving relative to one another. So our formula is the frequency of the observer, which is F sub O. And by the way, the subscript O is for observer. The subscript S is for the source. We're going to have to keep that straight. So the frequency of the observer equals the frequency of the source times the speed of the sound wave. So that's how fast the sound wave is traveling. So V is the speed of my sound wave plus the speed of the observer. Now, if the observer is stationary, that velocity is 0. But if they are moving, then we have to keep their velocity in here. So it's the speed of the sound wave plus the speed of the observer divided by the speed of the sound wave minus the speed of the source. One thing that we do have to be very careful of with these velocities are the signs. If the observer or the source are moving toward one another, so if the observer is moving toward the source, or if the source is moving toward the observer, we will give their values or their velocities a positive sign. Doesn't matter if it's moving to the left or to the right, to the east, to the west, up, down, whatever. If the observer is moving towards the source, their velocity is positive. If the source is moving towards the observer, its velocity is positive. If they're moving away from each other, their velocities are negative. So if the observer is moving toward or I'm sorry, if the observer is moving away from the source, then it has a negative velocity. If the source is moving away from the observer, it has a negative velocity. So we have to be careful of that because we've been ascribing positive and negative signs to the direction it's traveling. Now we ascribe our positive and negative signs to how it is traveling relative to the source or the observer. And we could have a situation, say we have an observer here and a source here. If my observer and the source are both moving toward each other, they're both going to have positive velocities, even though they're moving in opposite directions. So we have to be very careful about that. If I have another situation where I have my observer is going in this direction and the source is moving in the same direction but at a faster or slower velocity, then my observer here is moving towards the source. So it would have a positive velocity. But my source is moving away from the observer, so its velocity would be negative. Even though they're moving in the same direction, one has a positive velocity, one has a negative velocity. So we have to look at how fast or what direction these things are traveling relative to the source or the observer. Okay, this starts our final section of the PowerPoint where we are going to talk about resonance and standing wave. And one thing that I do want to talk about here is how waves interfere. We talked about the constructive and destructive interference of waves when we first started our unit on waves and vibrations. Sound waves can interfere with each other just like any other type of wave, and they can undergo both constructive interference and destructive interference. Now you're going to have constructive interference between two sound waves when the path difference between the two waves is 0 or some multiple of a wavelength. And what that simply means, and I'm going to try and draw this here, it's probably not going to turn out very well, but that means, if you guys remember, if we have one wave that kind of looks like this, I'm going to draw it, represent it as a transverse wave, even though sound waves are longitudinal, just because I think it's a little bit easier to see. If I have a second wave that is kind of going in the same pattern where my crests of the wave are going to line up with each other and the troughs of the wave are going to line up with each other, that's going to cause constructive interference. Now, if I take this bottom wave and I shift it over by some length that is equal to one wavelength, now instead of this crest matching up with this guy right here, this crest, if I move it over one wavelength, is now going to match up with that crest right here. We still have crest matching crest, and we are going to still have constructive interference. So the path difference is going to be the wavelength or some multiple of that wavelength. Destructive interference occurs when we have two waves and we have crests lining up with troughs of the waves, or areas of compression lining up with areas of rarefaction. So again, you can see here I have the crest of one wave lining up with the trough of another wave, the trough lining up with a crest here. That's going to give me destructive interference. Now again, if I take this bottom wave and I shift it over by any multiple of a wavelength, I'm still going to have crests lining up with troughs. So my path difference has to be some multiple plus 1/2 of a wavelength. It could be 1/2 of a wavelength. It could be 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths. It doesn't matter. It can go on and on as long as that we have a crest lining up with a trough. That will give us destructive interference. When we have a wave traveling through a medium and it hits some barrier or interacts with some barrier, sometimes that wave is reflected back into the medium, and it's going to be traveling in the opposite direction of the original wave. So what you have is a medium with waves traveling in opposite directions. And those two waves, the original wave and the reflected wave, are going to interfere with one another. And they follow, again, what we call the superposition principle. And I'm not going to get too deep into what the superposition principle is, but what it simply means is that when you have the two waves interacting, the resulting wave is going to be the algebraic sum of each of those two waves. So we just add the amplitudes of those waves up. And remember, if it's going up towards a crest, the amplitude could be positive. If it's going down towards a trough, the amplitude can be negative. If this is done at just the right frequency, it's going to cause the wave to appear to remain motionless or stand still. And this is what we refer to as a standing wave. Whenever you have two waves that are interfering with one another, and each wave has the same magnitude of displacement, in other words, their amplitude is the same, but the amplitudes are in opposite directions. So if I have one wave where the amplitude is going here, in that direction, and I have a second wave where the amplitude is in that direction, and if those arrows should be the same length. But if they have the same amplitude but in opposite directions, then the net result of that is going to equal zero. They're going to cancel each other out, and the net displacement of the standing wave is going to be zero. That's called a node. Now, the distance between nodes on a standing wave is going to be 1/2 of a wavelength. Where you have the standing wave where you have the maximum amount of displacement or the maximum amplitude of a standing wave, in other words, at the crests and troughs of the standing wave, you're going to have what we call an antinode. And then in the next slide, I'll show you graphically what that looks like. If I have a standing wave like the one shown in this diagram, my nodes are going to be at the point where the displacement is zero. So one here, there's a node here, a node here, and a node here. These are the nodes. My displacement for the wave at those points are zero, right? The wave is kind of smushed down to almost nothing. My antinodes are going to be here, here, and here. These are going to be my antinodes, and it's where I have the maximum displacement for my wave. So zero displacement, let me just highlight this, zero displacement here, 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 and here. Those are my nodes. My maximum displacement here, here, and here will give me my antinodes. Note a couple of things. Note that I have nodes at the ends because the string, in this case, the string is fixed and it can't move anywhere. And also note that my antinodes occur at every half wavelength. Let me just make some erasures here to kind of demonstrate this. Bear with me for a second. If I have one wavelength, which you start from here, oops, let's try this again, from here to here to here, that's one wavelength that I've just highlighted in yellow. Note that I do have antinodes every half of wavelength, one right here, and one right here. So I have a node every half of wavelength. I want to talk briefly about something called forced vibrations. All materials, all substances, all mediums have a natural frequency at which they like to vibrate. If I'm inputting a force or inputting energy into that system, and the frequency of the energy that I am inputting into that system is the same as the natural frequency of the medium or the system, it's going to cause that medium to vibrate and oscillate at a faster and faster rate. This is a phenomenon that is called resonance. So if the inputting frequency or the frequency of the energy being inputted into an object or a system or a medium is the same as the natural frequency of that medium or object or system, that will cause resonance. Some examples of resonance include pushing someone on a swing. We've all done that. And if you notice that if you push, you're not necessarily pushing harder every time they swing, but they go higher and higher the more you push. That's because the frequency with which you are inputting energy into the person is the same as the frequency with which they are swinging back and forth, right? They come backward, and then when they start to move forward again, you give them a little push in the back. And you do that at the same frequency with which they go back and forth, and that causes them to go higher and higher. That's resonance. If you've ever seen videos of people shattering glass with their voice, that's because the sound wave is at the same natural resonant frequency of the glass, and it causes the glass to vibrate until it shatters. Some other examples, and usually I would show you guys a video of this. You guys can look it up yourself. There's something called the Tacoma Narrows Bridge, which I think was in the 1930s, that was built out on the West Coast, and it was built in this little kind of narrow gorge. And what happened was that the wind that kind of funneled through this gorge was the same frequency as the natural resonant frequency of the structure of the bridge, and it caused the bridge to fluctuate and to vibrate wildly. Matter of fact, they had to close the bridge down when the wind got above a certain level, and at one point the wind got so strong that it actually caused the bridge to collapse. Luckily, and nobody was on it, so there was no loss of life. One other example of resonance is during the Loma Prieta earthquake in the 1980s in California. If you've ever seen that earthquake that happened during a World Series game, that's the one we're talking about. There was a highway in, I don't know if it was San Francisco or Oakland, I think it was Oakland, that was like, if you've ever been to the Mixmaster on I-84 in Waterbury, where you have one side of the highway directly over the other side of the highway. What happened was the frequency of the earthquake happened to match the natural frequency of the bridge, and it caused the highway to pancake down, and the top section smashed down on the lower section, crushing cars, and some of the cars were crushed to like about 12 inches high, if you can imagine that. Sadly, there were people in those cars, and there was a lot of loss of life. And that was actually, I think, the biggest loss of life in that highway happened on, or in that earthquake happened on that stretch of highway. So those are examples of resonance. Next, I want to talk about standing waves and harmonics. Typically, there is more than one frequency that will cause a standing wave in a medium. I know the top of the slide here says strings, but this applies to any type of medium. It could be air, it could be water, it could be any medium. So if there are multiple frequencies that will cause a standing wave in a medium, that series of frequencies is called a harmonic series. The lowest frequency that is in that series is what we call the fundamental harmonic, or F sub 1. So F sub 1 is what we call the fundamental harmonic, and that is the lowest frequency that will cause a standing wave. The next highest frequency is called the second harmonic, so we say that's F sub 2. And typically when you have a medium and you have a disturbance that's causing standing waves, the medium is going to kind of self-select only those frequencies that are going to fall within the harmonic series, and it's going to kind of damp out any other frequencies that are not within that harmonic range. When we have standing waves in air columns, and air columns occur whenever you have kind of a pipe or tube that has air inside of it. This applies a lot to musical instruments like trumpets, saxophones, trombones, things like that. Pipe organs, or I should say organ pipes, are another examples of that. So if you ever have a cylindrical tube and there's air inside the tube, that's what we're referring to when we talk about air columns. If one end of the air column or one end of the tube is closed, at the closed end you have to have a node, because the fact that the end is closed is going to restrict the movement of the air molecules at the end. If both ends of the tube or the air column are open, the air molecules have more freedom to be able to move around, and you have an antinode at both ends of the air column. So whenever you have an open end of a column of air, you're going to have an antinode, and whenever you have a closed end of an air column, you are going to have a node. If I have a tube that is open at both ends, so it's open at both ends, so I have antinodes at both ends of the pipe here. So if it is open at both ends, I know that the wavelength of my first harmonic is going to equal 2 times the length of the pipe. So my wavelength for the first harmonic is equal to 2 times the length of the pipe. And because I know that frequency, whoops, let me not write that in highlighter, let me put that in pen, because frequency is the wave speed divided by the wavelength, I know that the frequency of the first harmonic is going to be equal to the velocity or speed of the wave divided by 2 times the length of the pipe. For the second harmonic of a pipe that's open at both ends, the wavelength is equal to the length of the pipe. So because the wavelength is equal to the length of the pipe, the frequency of the second harmonic, I should say, is equal to the velocity divided by the length of the pipe, or 2 times the fundamental harmonic. For my third harmonic, the wavelength is equal to 2/3 times the length of the pipe. And because it's 2/3 times the length of the pipe, the frequency of the third harmonic is going to equal 3 times the velocity divided by 2 times the length, or 3 times the fundamental harmonic. So my second harmonic is double or twice the frequency of the fundamental harmonic, and my third harmonic is 3 times the frequency of my fundamental harmonic. When I have resonance in an air column that is open on both ends, I'm going to have a harmonic series of frequencies, and those harmonic frequencies are all going to be multiples of my fundamental harmonic. So they're all going to be multiples of the lowest frequency in the series. So I know that my frequency of a particular harmonic, and that n tells me which harmonic it is. Is it the first harmonic, second harmonic, third harmonic, etc., is equal to the number of the harmonic times the velocity of the sound wave, how fast is the sound wave traveling, divided by 2 times the length of the pipe. In an air column that is open on both ends, my fundamental frequencies can be any whole number, odd and even. So it could be 1, 2, 3, 4, so on and so forth. Now let's take a look at a tube that is closed on one end. Note here that when I close the tube at one end, on the closed end, I am going to have a node, and on the open end, I am going to have an antinode. For the fundamental harmonic, the wavelength of the fundamental harmonic is going to equal 4 times the length of the pipe. And again, because the frequency is, because the frequency is velocity divided by wavelength, the frequency of my fundamental harmonic is going to equal the speed of the wave divided by 4 times the length of the pipe. For my third harmonic, notice I don't have a second harmonic here. I'll talk about that in a second. But for my third harmonic, I know that the wavelength of the third harmonic is equal to 4/3 the length of the pipe. So the frequency of my third harmonic is going to equal 3 times the velocity divided by 4 times the length, or 3 times my fundamental harmonic. For my fifth harmonic, the wavelength of my fifth harmonic is going to equal 4/5 times the length of a pipe, or the pipe that the harmonic is occurring in. So the frequency of the fifth harmonic is going to equal 5 times the velocity divided by 4 times the length, or 5 times my fundamental harmonic. For resonance in an air column that is closed at one end, remember on the closed end we are going to have a node, on the open end we are going to have an antinode. The formula for calculating the frequency of a harmonic for a tube closed at one end is going to be the number of the harmonic frequency, or the frequency of that harmonic, is equal to the number of the harmonic times the velocity divided by 4 times the length of the pipe. A little bit different than the formula for a pipe that is opened on both ends. Very similar, but slightly different. And the frequency of the harmonic is also equal to the number of the harmonic times the fundamental frequency. One big difference with tubes that are closed at, or tubes that are open at both ends, is that when you have a tube that is closed on one end, you can only have odd numbered harmonics. So 1, 3, 5, 7, etc. There are no even harmonics in a column of air that is closed on one end. All right, guys, that's it for this PowerPoint. I understand some of this stuff can be confusing, but we are going to spend the next 2 weeks practicing these skills, going over lots of problems. If you guys have any questions at all, just shoot me an email, join up with one of the Google Hangouts. Remember, I am here for you pretty much 24/7 because I can't go anywhere. So just send me your questions and I will help you out as best I can. I'll see you in the next video.